Thermodynamics 1, Thermochemistry, calculating the standard enthalpy change for a reaction. In this tutorial, we will be looking at calculating the standard enthalpy change for a reaction, standard enthalpy change reaction example problems, a formula for calculation of the standard enthalpy change for a reaction, and finally, using the formula for the calculation of the standard enthalpy change for a reaction example problem. Goodness. Calculating the standard enthalpy change for a reaction. Here we have a chemical equation. Methane plus 2 moles of oxygen yields carbon dioxide and 2 moles of water. So step 1, write equations describing the formation of each species present in the equation above their standard states. These equations are called formation equations, and we just did that in the last video. Obtain values for the heat of formation for each of the compounds, and you'd find this in your AP Chemistry textbook. The elemental species, your free elements, like elements that exist by themselves or diatomics, have heat of formation values of 0 kilojoules as previously discussed, and no formation equation is written. That's super important. Let's do a couple of examples. Here's liquid methane. So for liquid methane, we'd have carbon as a solid plus hydrogen as a diatomic gas yields 1 mole of CH4 liquid. Now we have 1 carbon, 4 hydrogens, so I need 2 moles of hydrogen gas. And then I'd go to the resource that your teacher provides for you, and you would look up these heat of formation values, and this one is negative 74.6 kilojoules per mole. So do I expect you to memorize these? No, I do not. They would be given to you. Carbon dioxide. So again, we have solid carbon plus oxygen gas yields carbon dioxide gas. 1 carbon, 2 oxygens, 2 oxygens. Hey, that's done. That's awesome. And then we would look up the heat of formation value for carbon dioxide, and that is negative 393.5 kilojoules per mole. And then finally, water. So we have hydrogen gas plus oxygen gas to produce water. And we'll say this water is in the gaseous state. Now, can you have different heat of formation values for water in the gaseous state and the liquid state and the solid state? Yes, you can, and you have to be super careful about that. So let's go back. 2 hydrogens, 1 oxygen. So I have to put a 1/2 in front of this. And then the heat of formation is negative 241.8 kilojoules per mole. So fractional coefficients may be used to ensure that all product compound species are in their standard state of 1 mole. Absolutely super critical that everything is 1 mole as a product. So now we have all these heat of formation reactions. Step 2, manipulate the individual formation reactions to produce the original given equation. So if we think about what we just did with the formation reaction for methane, now we're going to take it and reverse it, and as a result, the sign on the heat of formation is switched. So CH4 gas yields carbon as a solid plus 2 moles of hydrogen gas. And now my heat of formation value is going to be positive 74.6 kilojoules per mole. So now we have the methane on the correct side as seen in our combustion reaction. We're going to do the same thing now for carbon dioxide. But it turns out for carbon dioxide, we don't have to do a thing because carbon dioxide is being formed and there's only 1 mole. So we're just going to recopy what we had before. So solid carbon plus diatomic oxygen gas produces carbon dioxide gas, and that heat of formation value stays exactly the same, negative 393.5 kilojoules per mole. Notice here that we skipped over the oxygen because oxygen is in its standard state and it would have a heat of formation value of 0, so no reason to include it. Last one is water. Now our initial heat of formation reaction for water was H2 as a gas plus 1/2 O2 as a gas yields H2O as a gas. What we want to do now, because we have a 2 in front of this H2O, is multiply everything here by 2. And when we do that, we'll have 2H2 gas plus O2 gas yields 2H2O gas. And our heat of formation value, remember, originally it was negative 241.8 kilojoules per mole. Now we're going to take that value and multiply it by 2, so our value would be negative 483.64 kilojoules per mole. Step 3, sum all of the 3 formation reactions. In other words, add them all together. In this process, some species may combine while others cancel. The objective is to have the formation equation sum to result in the original equation. So add together the heat of formation values for each formation reaction equation to determine the heat of reaction. So we take all of our equations that we had, we cancel out some values, combine other values, and then as a result, while at the same time adding together our heat of formation values. In the end, the 3 equations combine together to match the original equation. Methane plus 2 moles of oxygen yields 1 mole of carbon dioxide and 2 moles of water. And the overall heat of reaction, if we add this and if we add heat of formation 1, 2, and 3 together to get our overall heat of reaction at the standard state, is negative 802.3 kilojoules per mole of methane combusted. Let's do an example problem. Tetraphosphorus P4O6 solid plus 2 moles of oxygen yields P4O10 solid. So let's start out by writing the heat of formation reaction for P4O6 solid. So we're going to have phosphorus as a solid plus oxygen as a gas in its standard state, and give us P4O6 as a solid. So I need a 4 here and I need a 3 in front of the O2, and I have a standard state there. And then I would look up my value for the heat of formation for P4O6, and it would be negative 1,640.1 kilojoules per mole. Then, oxygen, no formation equation, not needed because oxygen is an element and it's in its standard state. So this, 0 kilojoules per mole. Not that we need to write it, but why not? And then finally, we have P4O10 as a solid. So just like we did above, phosphorus as a solid plus oxygen in the gaseous state yields P4O10 solid. So I'm going to have a 4 in front of the phosphorus. I'm going to have a 5 in front of my O2. And then I would go to my reference text and I would look up the heat of formation for P4O10, and that is negative 2,984 kilojoules per mole. Now that I have these heat of formation reactions, I can combine them together to figure out my overall heat of reaction. So the first thing that I'm going to do is take my formation equation for P4O6 and reverse it. P4O6 arrow 4P solid plus 3O2 gas, and that heat, that delta H1 was originally negative 1,640.1 kilojoules per mole. Now it's going to be positive 1,641 kilojoules per mole. For my P4O10, I'm going to write it just like I did for the original formation equation. So 4P solid plus 5O2 gas yields P4O10 when its delta H value, delta H2, that is not going to change from what we originally had, of negative 2,984 kilojoules per mole. Now I want to combine these two equations together to get my original equation that I had at the top of my previous page. So what can cancel here? Well, the 4 moles of phosphorus cancels with 4 moles of phosphorus. I have 3 moles of oxygen gas as a product and 5 moles of oxygen gas as a reactant. So I can cancel out these 3 with a leftover of 2 moles. And when I rewrite my equation, P4O6 solid plus 2 moles of O2 gas yields P4O10. I have my original equation. And then what I will do is I will combine my delta H1 and my delta H2 together. So my overall heat of reaction is equal to negative 1,343.9 kilojoules per mole. So that's another example of how to approach these problems. A formula for the calculation of the standard enthalpy change for a reaction. The delta H of reaction at the standard state may be determined by subtracting the enthalpies of formation of the reactants multiplied by their stoichiometric coefficients from the enthalpies of formation of the products multiplied by their stoichiometric coefficients. Wow, that sounds like a lot. Let's break this down. So the overall heat of reaction at standard state will be equal to the sum of all of the heat of formation of products, which will be given to you, minus the sum of all of the heat of formation of reactants at standard states, which will also be given to you. This relationship is included in the thermodynamics electrochemistry section of the College Board AP Chemistry reference tables. Let's look at an example. Determine the standard enthalpy change for the complete combustion of 1 mole of benzene, C6H6. So we're talking about a combustion reaction here of benzene. So of course we're going to start out with benzene, which is C6H6 plus oxygen, O2 gas, put a little G there, yields always carbon dioxide as a gas plus water. So this is a combustion reaction for 1 mole of benzene. So I know this has to stay 1 mole. So let's see how this works out. So 6 carbons, I need a 6 right here. Now my carbons are balanced. Next is always the hydrogens. I have 6 hydrogens. I need a 3 right here. 3 times 2, that'll give me 6 hydrogens right here. Now all I need to do is balance the oxygens. So 6 times 2 gives me 12 oxygens out of my carbon dioxide. 3, oh, there's a subscripted 1 there. That's 3 oxygens here. That'll give me 15 oxygens altogether. Now, I could go back if I wanted to say, oh, I can't have any fractions in my balanced chemical reaction and double everything. But remember, this is a Hess's law problem, and ultimately, the oxygen is not going to be taken into consideration because it's in standard state. So I'm okay doing 15 over 2 here and not worrying about the oxygen because ultimately, this is going to be represented as a 0 anyways. So now what I want to do is I want to take these reference numbers, which would be given to you, or you would be able to look these up in your textbook and substitute them into this formula. So the first thing we're going to do is take the sum of the heat of formation of the products. So I have 6 moles of carbon dioxide plus 3 moles of water. So that's the sum of my products minus the sum of my reactants. Now, I'm going to disregard the oxygen because I know that's already going to be 0, and I have 1 mole of the benzene. So 1 mole of the benzene, C6H6. Now that I have this set up, I'm going to take my reference numbers that are given to me, and I'm going to replace my formulas with those reference numbers. So sum of 6 times negative 393.5 plus 3 times the heat of formation for water as a liquid. Be careful here. Water can also be represented as a solid and a gas, so make sure you have the correct number and don't drop the negative. So negative 285.8 kilojoules per mole. Should be writing that in. Okay, minus my 1 mole of benzene. I'm not going to put the 1 mole in, so that's 49.1. And then I'm going to work this all out. I'm going to multiply together the 6 times the 393.5 plus 3 times the negative 285.8. I'm going to get an answer there, and then I'm going to subtract 49.1. And if I do that, the answer that I get is negative 3,267.5 kilojoules per 1 mole of benzene. And that number is going to equal my heat of reaction at standard state for the combustion of 1 mole of benzene. So what did you learn? We talked about calculating the standard enthalpy change for a reaction. Standard enthalpy change example problem, did one of those. A formula for the calculation of the standard enthalpy change for a reaction. We're going to do a lot more of those in class. And using the formula for the calculation of the standard enthalpy change for a reaction example problem. Need more help? Feel free to contact me. Have a great day.